Hey guys, welcome to my channel. So my last video I kind of had this apart and showed how I basically built it and some of the components involved in it. And this video I'm just going to do kind of a summary of what I tested out. These are all the different rotors. So this was the original one I designed for it with the slip rings and everything. I just used little key slots to do those, where they could be removed. And then I have the stainless steel piece in the middle because these are set up in bucking, so this regular steel in the middle wasn't working, so I added the stainless steel, which really helped a lot. And yeah, so I tried this out in there. Some of the issues that were involved were brushes. I've made a couple brush motors, but I didn't realize how much resistance are in these little brushes. So it was kind of interesting because when just measuring the rotor, as this was set up like this in the motor, this had 1/3 the power as the stator windings, even though they're wound exactly the same amount of turns and everything. And the motor wasn't running right, and finally measured it down, and it was actually these. So I took that off and I went for a simpler approach, with just copper buses. These are 10 gauge solid copper. And it actually worked really simple, just soldering onto these and screwing them on. But obviously these weren't independent, so one would I had them right here with the rubber band pulling them back, and worked okay, but they needed to be independent because these brush contacts are just a little bit off because they're just handmade. So I made this one so that these can independently be moved, and I just hooked a rubber band from here to here, and they would keep the tension on it. And just a small amount of running, you could see how much wear actually happens. But the point is, these actually provided plenty of current to make this run, and it actually ran pretty decent. And I started comparing it to other rotors. So I started with this, and one other thing that was kind of interesting is I had these are in series, and then these are in series, and I had them both parallel ran. So if one of these didn't make contact, it wasn't enough power for this. The rotor would actually go backwards in a traction mode. So it actually, without enough power on these, this actually turned into an attraction mode like this. And so that was really interesting. So the better way to do it is keep these in parallel, those in parallel, and then go from series, from stator to rotor, to make sure everything's balanced out. And that makes a big difference with it, because if these aren't equal, then you get the traction of the steel involved, and it just turns into a traction motor. So after that one, I tried this one, and I used these little optical timing, just like how that's set up. And these are a couple different thicknesses, so shorter on time, more on time. And this one ran really nice, really smooth, no magnetics, so it's just really smooth. And then I used this one, which was even smoother, but the traction motors use a little bit more power because it has to magnetize the rotor, but they run so smooth. And then the third one I tried was this one. This is actually neo magnets, really strong ones. And these are actually probably 22 years old, but they're still so strong. And I taped them down and everything because they want to separate. They're the same polarity. So when I did these, I actually changed the polarity on this. I made it to where it's north and south, where right now, for how it's set now in this was on repulsion. That was on repulsion. And it's interesting because it will still run even though they're on the same polarity with the traction motor, just not as strong. So once I switched one of the coils around, then this ran really nice. And then this is what I ultimately use that's running right now. It's just 3D printed rotor. It has 4 of the neo magnets that I used on my Bedini motor, and that's what's in here right now. And this one actually performed the best. I still need to add 2 more coils, top and bottom, to give it more torque, but just 2 coils. I threaded the coils to where you could just unscrew them, take them out, and that worked really well. And so yeah, it was quite interesting seeing how all these different ones worked out. And this one ultimately worked the best. This one was really fast, but there was a big gap. It was about an inch gap between the magnets, and this one's about a 1/4 inch. The magnets are smaller, but they're plenty compared to the steel, so that one worked really nice. So right now we have it set up at 24 volts, and I have my MOSFET 24 volt system with the pulse width modulator, and then it goes into the cap dump. The cap dump is set to trigger at 36 volts, and then it's going to the second battery. So right now this is firing at 36 volts, and you can see it right here on the screen. And so it fires at 36 volts into this battery while it's running off this one. And right now it's just kind of like an idle speed, but you can see on the scope it's chopping it up a lot. So we're getting quite a few pulses. I mean, right now we're using less than a 1/2 amp, and we're pulsing about 3 amps every other second. So this, I did the speed control so we could adjust this, so this actually can start going up pretty quick. So at full power it's humming pretty good. It's about 3 amps and it's quite a bit of torque. So you can run it all the way up to about 8 amps, probably 12 to get it to stall. But here's the waveform at full power. So it runs really smooth, and see how fast it's charging now. So these batteries are starting to get up there. So almost 15 volts on each one at 30 volts. So we could just back this guy off. But what's nice is the pulse width. You can make it kind of like oscillating Bedini motor. You just turn this down, do about 1 amp right here. You still have good usable torque. You still have good charging. So yeah, pretty neat. So if you guys have any questions, leave them in the comments. Thanks for watching.